This lecture will cover the concept of periodic trends, kind of along our same theme of using the periodic table as a resource. And so here's what you're going to need to be able to do following this lecture. Identify and explain these periodic trends. So there's two parts to what you need to learn. First, you need to know the trend itself, how you would be able to compare values for two different elements on the periodic table, but then at a higher level being able to explain why that is the case. So we'll be looking at both of those factors. And here are the trends. As you can see, atomic size, that's sometimes called atomic radius as well. We'll be looking at ionic size, so looking at comparing ions to their regular atoms, ionization energy, and then electronegativity. And so we're just going to dive right into it. Each trend is somewhat self-contained. So again, we just need to learn each trend and then be able to explain it. So first is atomic size. And so this is actually a little bit of a schematic of the periodic table. What you can see is the bubbles there representing atoms increase going down a group or down a family. So this would represent, sodium, and then say potassium, and then further than that, say rubidium. Those are larger as you go down. And then the next size is a little bit tough. So let me explain what I've done here. The arrow represents how the size increases, but as you move from left to right, so going this way across a period or a row on the periodic table, the size actually gets smaller, and so we'll explain why that's the case. It's a little bit, maybe a little bit tricky of a concept, but not too bad. So again, this is the trend to know. So in general, atoms get bigger going right to left and then top to bottom. So here's why. We're here comparing sodium to magnesium, so this is the period trend, so going from, say, left to right. And I've made these images representative of size a little bit in magnesium, even though it has an extra electron and an extra proton, is smaller. And the reason for that, it's called effective nuclear charge, or what we're doing here is we're comparing this relative strength of the protons to the electrons that surround them. So with sodium here, we're in the third energy level, and if you remember from some of our previous work, we're in the 3s energy level. And so there's 11 protons and 11 neutrons, and that last proton is just on the outer level here. So then, and it's that certain distance away. What happens when you add magnesium, you add one more proton, and that same electron is the same distance away. So these protons down here are exerting what's called a stronger effective charge. There's less, I guess you'd call it shielding. So these electrons are pulled more tightly. They feel more strongly this pull because there's one more proton within, or it's pulling against the same distance. All right, so over here you've got 11 protons and these 11 electrons, and it's at this distance away, the third energy level away. But here your electrons are still only that third energy level away, but you've got 12 protons pulling on them, so they get pulled in more tightly. So again, the trend is that as you move from left to right on the periodic table, the size gets smaller. The trend for a group is a little bit easier to, I guess, comprehend. Comparing, say, sodium to potassium, when you go from sodium in the third outer energy level to potassium with the fourth outer energy level, that extra shell is larger. So what you've got there is the 4s compared to the 3s, and so it's, well, just bigger. The fourth energy level is larger, and so that size renders it bigger. Also, you can see that there's just more stuff in the way here, so the shielding is much greater. The electrons are shielding these outer electrons, so they pull out a little bit further. So again, the trend that atoms get bigger as you go down a group. The next trend is going to be for ionic size. So we've moved out of atomic size, now we're into ionic size. Again, we're just going to go through these pretty quickly here for what's the basics, and we'll do most of our practice in class. Here, ionic size is comparing here chlorine with its 17 protons. That's also going to have 17 electrons. You can see it's got these 7 outer electrons here. A chloride ion is going to have an extra electron. So you can see that there's an extra electron added here. So this is the addition. So now, maybe similar to what we talked about before, over here you've got 17 protons, 17 electrons. And so they have that positive negative attraction, and they're somewhat held with a certain amount of strength. Now over here you've got 17 protons and 18 electrons. So the effective charge that each electron feels is a little bit less. So instead of being 1-to-1 like it is over here, it's 17 protons to 18. So it's a little bit less than 1 proton of charge per electron. What that means is that they feel a little less of that positive negative attraction, and so they spread out a little bit more. So the trend, or the rule that you need to know, is that anions, those are negative ions here, then 1 minus, those are larger than their neutral atom. So this is the neutral atom chlorine, this is the anion, or the negative ion, and it is larger. Looking to periodic trends for cations, or positive ions, you've got a sodium atom with 11 protons and 11 electrons, and then you've got the sodium ion. Now a cation is positively charged, so you've only got 10 electrons here. So in this case now, it's the opposite. You've got 11 protons versus 10 electrons. So over here, again, it's a 1-to-1, 1 proton to 1 electron pull. Over here, you've got 11 protons to 10 electrons, so there's a little bit more than 1 proton of charge per electron, and that draws them in a little bit more closely. They have a stronger attraction. So they're drawn more closely to the nucleus. And you can see by the size of the image here, they're just smaller. So your rule to know is that cations are smaller than their neutral atom. So you'll need to be able to tell the difference between, say, a cation compared to its neutral atom, and then an anion compared to its neutral atom. The next trend that we'll be looking at here is ionization energy, which, as a definition, ionization energy is right here. So here's an outer electron, a valence electron. It's attracted to these protons, it's part of this atom, but sometimes these can be plucked away, they can be taken off and taken to another atom or whatever it is. The energy needed to overcome this attraction is called the ionization energy. It's a measure of how strongly this outer electron is held to the nucleus. So the trend itself that we'll be looking at is represented here, and so we'll take a moment here to dissect this graph. The helium, neon, argon, those are shown to give you some perspective here. Notice ionization energy versus atomic number. So these are the first 18 elements. So number 1 would be hydrogen, 2 of course lithium, 3 lithium, and so on. So 3 helium. Sorry, got that messed up. 1 hydrogen, 2 helium, 3 lithium, and so on. Then you've got carbon, boron, all that. And I put the periodic table down here for reference. So what we need to figure out is the trend first, say for a period. So let's start here, going from lithium all the way to neon. So here's lithium. Notice that the trend is increasing. It's not a perfect line, but it's increasing in general all the way up to neon. And the reason for that is electrons, or atoms, to be stable will want to have a full valence shell. So down here, this has 1 valence electron, this has this has 1 valence electron, this has 2 valence electrons, this one has 3. So it's almost easier for these to lose their valence electrons, and become positive ions than it is for them to gain more. So if we're measuring how hard it is to remove an electron, these ones are going to want to get rid of them because it's more stable for them to get rid of them. Whereas as you get closer here, these elements are much more close to neon, which is a complete S2P6 configuration. So that's a stable noble gas. So something like, say, fluorine right here, it's not going to want to lose an electron, it's going to want to gain an electron. So this, say if this was fluorine's last electron, it's not going to get rid of it, it's going to hold it because it wants to get closer to that neon configuration. So as you go from left to right, it increases more and more. Now we can also look at it by group. So I think it would be easiest here. We could look at, let's go with the noble gases would be fine. You've got argon, then you've got neon, then you've got helium. Okay, so you can see that that is increasing in general as you go back up a group. So, and then helium. We can also, and then neon has a higher ionization energy, and then helium. We can also compare, say, group 7, which would be chlorine and fluorine. Here's chlorine. Ionization energy increases. And the reason for that, the higher you go up a group, the ionization energy increases. And the reason for that is that they're smaller elements. So smaller elements are going to hold on much more tightly to their electrons just because they're closer to the nucleus. So you could see here, you know, this has a certain number of electrons. This outer electron is held somewhat strongly. But if there were more and more shells in between and the outer electron was, say, up here somewhere, it's going to feel the pull of this nucleus a lot less strongly. Even though it might be close to its noble gas configuration, it's just going to feel it less, say, than a smaller atom would. So the trends to look at, we're going to flip to a different slide, is right here, where you have the trend increasing going up a group, and then it also increases going across a period. So your general trend is sort of diagonally and up to the right. You'll notice that's opposite of atomic size, and that's not really a coincidence because these are smaller atoms up here, so they're going to be holding on to their electrons much more tightly. The final trend that we'll be looking at is electronegativity. Now, electronegativity is very similar to ionization energy because it's talking about the attraction of electrons to a compound, or attraction of electrons to a nucleus, I should say, but it's comparing the two when they're in a compound. So for example, this is a bond between oxygen and hydrogen. Oxygen, you can see these dots represent the electrons. More of the electron dots seem to be concentrated around oxygen than around hydrogen. So if we were comparing these two, it's almost like a tug-of-war. It's the pull of electrons in this compound, so where do they tend to end up? Over here. So oxygen has a higher electronegativity than hydrogen. The trend for that is actually the same as ionization energy with one little exception, and I'll talk about that in just a minute. Notice as we go up a group, there's a slight increase. Even this one here is kind of minor. Let's go over here. The increase in group 6, notice it's stepping up. So there's much more attraction with oxygen than, say, polonium. Or moving over here, you've got astatine compared to fluorine. And again, the reason for that has to do with size. The other part of the trend would be going from left to right on the periodic table. So as you move from left to right, the trend generally increases because these are much more close to having a noble gas configuration, and so they're going to hold on much more tightly. And so again, this is just a visual. Also noble gases. We leave those off because noble gases already have their S2P6 outer configuration, and so they actually don't form bonds. And since electronegativity has to do with the attraction of electrons within a compound, since noble gases don't really bond to a significant degree, they're left off that list. They have almost a zero value for electronegativity. So again, here's the trend in a little bit more clean format. It increases going this way from left to right, and then it also increases going up a group. Again, the trend tends to omit noble gases because they don't have much of a pull for electrons in a compound. So to recap what we've looked at here, we looked at trends. You needed to know the trend and then also be able to explain why that trend is the case, or why it is that way. So you've got atomic size, you've got ionic size, ionization energy, and electronegativity. And that's it for periodic trends.